You know the game Candyland? Board game for toddlers where you draw a card from a deck to reveal what color square you go to on a board themed around unhealthy snacks? No strategy because the game is predetermined by the cards before you start playing? Well, what if it were even worse? That was the question asked by the YouTube channel No Rules Barred in their series House Rules.
How are we changing Candyland, Sullivan? I'll tell you how we're changing Candyland. We have to correctly guess what colour is going to come up before we turn it over. Only then can we move to the space indicated on the card.
That sounds worse.
We've somehow managed to make Candyland worse.
While these changes do make the game much more unpleasant, they do add one thing: the potential for strategy. So if you had to guess what the next card is, and there's a 1 in 6 chance of it being any given color, what color should you pick? The obvious answer, and the strategy quickly taken by both hosts, is to guess the color that will put you furthest ahead.
I'm going to go for blue first.
Blue, eh?
Yep.
I see what you've done there, you little cheeky boy. Because this little blue square leads you immediately to a shortcut, doesn't it?
Oh, well, you know, I'm going to go for blue again.
For blue? That is a blue.
You know what colour I'm going to say?
What's that, Sullivan?
It's going to be a blue.
It's going to be a blue. Blue.
New deck, new me. And I'm going to go for blue.
But remember that asterisk on 1 in 6 chance? Well, there are also 5 sweet cards: peppermint, gumdrop, truffle, lollipop, and ice cream that take you to a specific spot on the board. So though it's very unlikely, a 1 in 35 chance, if you correctly guessed ice cream at the start of the game, you'd be taken almost to the end of the map. Of course, besides the sweets, there's another asterisk on the 1 in 6 chance. To move forwards, you just need to guess the right color. But there are 2 kinds of cards of each color: a regular card, which takes you to the first square of that color ahead of you, and a double card, which takes you to the second square of that color ahead of you. So a single orange card will take you to square 5, but a double orange card will take you to square 11. And beyond that, there's yet another asterisk on the 1 in 6 chance, and in fact every chance involving a deck of cards. When you draw a card of one color from the deck, it's now less likely for subsequent cards to be that color. An example for clarity: imagine a deck of 12 cards, 2 of each color. This means there's a 1 in 6 chance of drawing a yellow. Then, you draw a yellow. Now there's just a 1 in 11 chance of drawing a yellow, but a 2 in 11 chance of drawing, say, a purple. Of course, given the size of the deck, it's fairly hard for a human to keep track of the number of cards of every color. But who said the player is a human? Well, I guess I did when I told you to imagine that you're playing this game. I assume you're human, unless you're watching this way in the future and raccoons have become the dominant race or something. Well, human or hyper raccoon, you probably can't remember the frequency of all those different cards, but a computer absolutely can. This extra piece of info unlocks new, probably better, strategies. For instance, you could try to move forwards on as many turns as you can, not caring how far you go. In that case, just pick the color that's most frequent in the deck, and as such most likely to be drawn. If there's a tie, guess the one that will take you further. So we have a strategy that tries to go as far as possible, not caring how likely the guess is, and a strategy that guesses the most likely card, not caring how far it will take them. Surely a medium between the two would be better. Think about the ice cream card. If you guess ice cream at the start of the game, there's a 34 in 35 chance you don't move at all, but a 1 in 35 chance you move ahead 63 spaces. If we multiply the probability of each result by the number of spaces you move, and then add them together, we get the expected value of guessing that card. The algorithm can calculate the expected value of guessing each color, and then guess the color with the highest expected value. These are the results for the very start of the game. Of course, this is too much math for a human or even a hyper raccoon to do in their head every single turn. But what about a strategy so simple, you don't need to make a single calculation, only need to remember one thing, and don't even have to know what the board looks like? I'm of course talking about guessing the same color every time. Since the game ends on a multicolored rainbow space, it doesn't matter which color you pick, as all of them can reach the end, though some can reach it faster than others. In the 2021 edition, the version of the board House Rules played, the first blue square is a very long shortcut that bypasses much of the board. So you only need to draw blue 9 times, while most other colors require you to draw them 14 times. So now that we have our algorithms with varying amounts of good strategy, it's time to test them. How good are they at Candyland, but somehow worse? To do this, first we need to make a Candyland board. Well, I need to make a Candyland board. You don't have to do anything. This Candyland board, rather than a colorful, visually appealing path made of sugary gumdrops, is a list made of numbers. Each index on the list tells you what color it is. This is all we need to figure out how much farther the player goes. For instance, if you're on a red square and you draw a single orange card, you always move 4 squares ahead, no matter which red space you start from. Except this isn't exactly the case. There are also the pink spaces with sweets on them. Won't these mess things up? Well, no, because these squares aren't really squares.
But this delicious
Square.
is not
square. There's only one way to reach the pink squares, by drawing the specific sweet card. Because Candyland uses color cards and not numbers, these spaces function identically to the ones directly before them. Whatever card you draw, you end up in the same space whether you start on the peppermint or on the purple square behind it. Thus, we can represent the peppermint space with that purple square. Drawing the peppermint will bring you to that purple square. Drawing the color you're on takes you ahead 6 spaces, since there's a repeating pattern of 6 colors. And since drawing double cards is like drawing that color and then drawing it again, we can treat double cards like single cards, but just add 6. There are still some special cases. The rainbow space is different. For instance, if you draw orange and you're at this orange space, you don't go ahead 6 spaces, you go ahead 2 spaces, reach the candy castle, and win the game. Of course, since you win the game, it doesn't really matter how many spaces you go. We can represent the candy castle by not representing it. If we end the list right before the rainbow space, we can easily see if a player has won by checking if the index they're supposedly at is within the size of the list. If their index is beyond the list, that means they've won. If their index is before the list, that means I made some stupid mistake while coding. As previously mentioned, the board contains 2 shortcuts. If the player lands on this blue or this green, they get taken all the way to this blue, or this green. Now, since every time a player lands on the square, they get taken across the shortcut, the player is never going to actually end their turn on this space. So at the end of each turn, we can check if the player is on this space, and if so, move them to the corresponding shortcut. One last special case. Remember what I said a minute ago about pink spaces not being spaces?
is delicious.
Square.
Is not
Square. 4 of them are just inserted between 2 squares, and we can ignore the pink. But there is one exception. The truffle is right in front of an orange and behind a red. But red is never 1 square in front of the orange anywhere else on the board. It's always 2 squares ahead. Green is usually right after orange. The truffle completely skips a green spot. So, in all these spaces, picking green will take you 6 further than would be expected given the color. So, how do we deal with this? Same way we deal with these spaces. If you pull a green on them, you'll go 6 spaces further than expected, because of the shortcut. So we'll just treat the truffle space as a green space, but a shortcut to the next green. Incidentally, this means that if our one color algorithm always gets green instead of blue, it would need to be right 12 times. Still more than blue with 9, but less than the other colors, which take 14. There are also licorice spaces, which make you lose a turn if you land on them. In the event that a player does land on one, they get marked as having been licoriced. Whenever it's a player's turn, check if they've been licoriced. If so, then skip their turn and unmark them. To make the board actually playable, at least for computers, I'm not making UI for human players because why would I ever want to play Candyland? We need to make a deck of cards. Not real cards, just a list containing every card to accurate proportions in random order. So 3 single cards and 2 double cards of each color, and 1 card for each of the suites, for a total of 35 in a randomized order. We use a variable to keep track of where the top of the deck is, and when we reach the bottom, shuffle the deck again. We have a board, cards, and players, but we still need one more thing to play the game. The ability to actually play the game, turn taking. We could have one player repeatedly guessing a color, drawing a card, and moving forwards until it wins, but that's not the real Candyland but somehow worse experience. For instance, with one player, if you repeatedly guess ice cream, you're guaranteed to get it before you go through the entire deck. But with 2 players, there's a 50% chance your opponent will draw ice cream instead of you. Games should have 2 players, to most closely simulate the House Rules episode. But we also want to see how long it takes for even the weakest algorithms to win. And if they're playing a stronger algorithm, they probably won't win at all. To fix this, I've made an even weaker algorithm. A player who will never correctly guess the card, no matter what. Which also pretty closely simulates the House Rules episode.
You haven't moved this entire game!
Of course, this algorithm isn't just unlucky. It's literally impossible for it to guess the right color, because it isn't even guessing a color at all. This way, an opponent will draw cards, but the player will still win eventually. Now, I did just say we have players, but we really don't. We just have strategies. I had to actually implement the algorithm to make them play. The blue player was easy to make. It just always guesses blue. The only problem with it was that I had set up shortcuts incorrectly. So when it landed on the first blue, instead of taking the first shortcut, it took all of them and ended up halfway across the board. But other than that, it was smooth sailing. I even implemented a second algorithm like it that only guesses purple, just for fun. The far algorithm is also fairly simple. Ignoring shortcuts and suites, the color that would take you the farthest is always the color of the square you're already on. If it's within range of the shortcut, it will aim for that. Of course, that depends on what's in range. If right before a shortcut, a single green will take the player farther than any other single card. But it still won't take the player as far as any other double card. To resolve this while keeping the algorithm simple, we'll split it into two strategies. One that assumes all cards are single, and one that assumes all cards are doubles. Assuming all cards are single, you should guess green on these spaces, and guess blue on these spaces. Assuming all cards are doubles, you should guess green on these spaces. Assuming all cards are doubles makes it impossible to reach the blue shortcut, so we can just ignore it. Everywhere else, just guess the color of the square you're on. These algorithms were also easy to implement. It's worth noting that the far doubles algorithm will only ever guess green, as that's the furthest color from the start, and all subsequent shortcuts are green. It only ever guesses one color like the blue algorithm, except it's actually making decisions based on where it is on the board. Bad decisions, as it makes a silly assumption about all cards being double, but decisions nonetheless. Speaking of making silly assumptions about cards, we've been ignoring the sweet cards. Well, unlikely, drawing the ice cream early in the game would definitely put you farther ahead than any other card. If you're further ahead, it may be less useful than other cards, or even send you backwards. So if a color would put this algorithm further ahead than pulling a sweet, it won't get that sweet. Once again, we run into the problem with double cards, so once again we're splitting this into two algorithms. One that assumes all cards are single, and one that assumes they're all double. Of course, even if you are behind, guessing ice cream is only useful if it's actually in the deck. Otherwise, you're guaranteed to move 0 spaces. So far, these algorithms haven't been calculating probability, as they're supposed to be strategies a human could use. But since there are only 5 sweets, and each one is either in the deck or it isn't, keeping track of whether each one has been drawn seems reasonable. So this algorithm checks if it's far enough behind to bother with ice cream. If so, it checks if there's still ice cream in the deck. If so, it guesses ice cream. If not, then it checks if it's far enough behind to try for a lollipop. If so, it checks if there's still a lollipop in the deck, and so on for each sweet. If it's too far ahead for any sweets, or all the sweets have been drawn already, then it just carries out the regular far algorithm, either single or double.
Segue.
The likely algorithm makes more use of memory than the sweets algorithms. It goes through each color, checking which one is most frequent in the deck. If multiple colors are equally frequent, it picks the one that will put the player farther ahead. And once again, we'll split this into two algorithms, one that assumes all colors are single, and one that assumes all colors are double. This won't make too much of a difference though, as this algorithm usually doesn't care about how far it goes. If it turns out there's only one of the most frequent color, then it goes through all the sweets, similar to the sweets algorithms, and picks the one that will put it furthest ahead. Now, this is a fair bit of stuff to do every time we want to draw a card, which could be slow if we want to have, say, 1,000,000 games to find out how long it takes each algorithm to win on average. Fortunately, we don't need to do this every time we want to draw a card. Once we've found the most likely color, it's only ever going to get more likely to be pulled as the deck gets smaller. A 5 in 20 chance is greater than a 5 in 35 chance. The only exception to this is if the color itself gets drawn. This decreases its frequency, which may make it less likely to be pulled than another color. So we can have the player remember the most likely color and only ever recalculate it if that color gets drawn. I actually had a bit of trouble with this one. Not with the whole only remember the most likely color thing, that part was easy. I actually just forgot to have the memory change whenever a card gets drawn. So it always thought there were 5 cards of every color, and as such just acted exactly like the FAR algorithm. So with that out of the way, time to implement the most complicated strategy.
Segue.
While the strategy is much too complicated for a hyper raccoon to do in their head, it was pretty simple to implement. The likely algorithms already had a working memory of the relative frequency of cards, so I just had to multiply the frequency of each card by what space it would put you on, adding together the doubles and singles of the same color. That's right, finally an algorithm is complex enough to acknowledge both the single cards and the double cards at the same time. Technically, for expected value, you're supposed to use probability, not frequency, but since the denominator is the same for everything we're comparing, it would just be a waste of time. Speaking of wasting time, remember the liquid spaces that make you lose a turn? Just like all the previous strategies, the expected value algorithm completely ignores the liquid spaces. This is because losing a turn doesn't really matter much when you only have a small chance of moving every turn anyways. We have all our players, let's see how they do. We'll run 1,000,000 games between each player and the dummy, recording data for each game. These being, how many turns it took the algorithm to reach the end. This one is pretty self-explanatory. How far they got by turn 29. In the original House Rules video, they didn't play a full game of Candyland but somehow worked to completion. See, one additional rule I didn't mention earlier is that every time they guessed wrong, which was often, they had to take a shot of sherry. They agreed to end the game when they finished off the entire bottle.
I think maybe we make a rule.
What's that?
That if we get through the bottle of sherry, it's whoever's closest wins. That's fair.
which happened after 29 turns. So to fairly compare these algorithms to the hosts, we need to use their position at the point the host stopped. Of course, if you've seen the video, you'll know the hosts weren't the only ones playing the game. Their camera operator Terry guessed 2 cards, and was correct once.
You guys are really bad.
Let's bring Terry back.
We'll bring Terry back.
We'll bring Terry back.
We'll bring Terry back.
Have a little go.
Okay. Terry gets to have a little go.
Presumably, yeah. Why don't you have a little guess, Terry?
All right, Terry. Let's hear your guess, shall we, Terry? What's your guess for the next card,
What's
Terry?
your little guess?
What's your little guess,
What's
Terry?
your guess?
Terry, Terry, let us know your little guess, Terry. Yellow.
eh?
Oh, Terry, here you go.
I'm furious! I'm absolutely furious!
So we will also record how far each algorithm gets after 2 turns, to compare them with Terry. Along with how far they get, there's one other stat we'll have. How many incorrect guesses they made. Basically, how many shots they'd take. So, without further ado, here are the results. The algorithm that did the worst with the longest average game was, of course, the purple strategy, taking an average of 70 turns to win. It guessed correctly 14.5% of the time. If it were playing on house rules, with the game ending at turn 29, it would have beaten Adam 35% of the time, and beaten Sullivan 94% of the time. And this is the worst one. By turn 2, it only beat Terry 1.2% of the time. Blue was much better. Its accuracy was about the same, obviously, since there are the same number of blues and purples in the deck. But games on average only lasted 55 turns. It beat Adam 75% of the time, Sullivan 99.7% of the time, and even beat Terry 27% of the time. Which makes sense. If the algorithm moves at all, it's already beating Sullivan and Terry. Far is a bit better than blue, since it can take advantage of the green shortcuts. Its games lasted an average of 54 turns. It was accurate 15% of the time, because really, all of these algorithms with no memories just have a 1 in 7 chance of guessing right. It beat Adam 80% of the time, and once again beat Terry 27% of the time. The beating Terry percents being the same makes sense, given that at the start of the game, Far is always guessing blue anyways. Far doubles, on the other hand, always guesses green, which makes it even worse than blue, with an average game of 63 turns. It only beat Adam 67% of the time, and Terry 11%. Sullivan even has a chance, only being beaten 98% of the time. Speaking of having only around a 2% chance of success, let's see how the algorithms that always guess ice cream did. Sweets took 37 turns to win, and had an accuracy of 11%. But despite this low accuracy, this algorithm actually made the fewest wrong guesses so far, since its games ended so quickly. It beat Adam 84% of the time, a new record. But although this algorithm is the best so far against Adam, it's also the worst so far against Sullivan, only beating him 92% of the time. This makes sense. While this algorithm can get very far ahead, it usually spends quite a while at the start, just waiting for ice cream. For the same reason, the algorithm didn't fare well against Terry, only beating her 6% of the time. Sweet's doubles once again did worse than its single equivalent, with games lasting 54 turns and having an accuracy of just 9%. It beat Adam 78% of the time, Sullivan 87% of the time, and Terry 3.1% of the time. And now moving on to the big boys. The likely algorithm took 38 turns to win, beat Adam 92% of the time, Terry 26% of the time, and Sullivan a whopping 99.95% of the time. New records all around. The likely doubles algorithm did much worse. Granted, Sullivan still has no chance, but average length was 43 turns, it beats Adam 88% of the time, and Terry 12% of the time. Both likely algorithms have an average accuracy of 25%, giving them both the highest accuracy and the fewest wrong guesses. So far, at least. And last but not least, or maybe it is least because the goal is to make the game shorter, the expected value strategy. It had a slightly lower average accuracy than the likely algorithms, but made up for it by going farther on average, with its games only lasting 34 turns. It beat Adam 95% of the time, Sullivan 99.8% of the time, and Terry 27% of the time. Which actually isn't the best. Well, it is the fastest game, fewest wrong guesses, and most likely to beat Adam. But the likely algorithm gave Sullivan the least chances of winning. Which makes sense. The EX algorithm prioritizes going far at the cost of accuracy, but you don't actually have to go far to beat Sullivan. And what algorithm is better than EX at beating Terry? Why, it's the cheeky little boys themselves, blue and far. See, if 2 blues were already drawn from the deck, EX would be inclined to guess ice cream, as it being so far ahead gives it the highest expected value. But to beat Terry, you don't need to be so far ahead, You just need to pass square 9. And what color takes you past square 9? Why, blue, of course. Either single blue, due to the shortcut, or double blue, which takes you to square 10, just edging out Terry. Since Fire doesn't care about sweets, and Blue only cares about, well, blues, they both would always guess blue at the start, and as such were slightly more likely than EX to beat Terry. So, if this Christmas you want to play Candyland but somehow worse, which you shouldn't, drink responsibly this Christmas. Which, if you're at the age where you'd willingly play Candyland, means not at all. Now you know, the best strategy is probably too complicated for you to do in your head. But if you're only playing 2 rounds, well, just keep guessing blue.